Assalamu alaikum. This is lecture number 4, Physics 731. In this lecture, I will solve Laplace equation in cylindrical coordinates using series solution method. Our equation is del square phi equals 0. Del square is the Laplacian in cylindrical system, which is given by this expression. We will use separation of variables. We assume phi is equal R capital times Q times Z capital. Now we substitute phi in this differential equation and divide by phi. We get this equation. Now the Z capital part is already separated. We call it K square, where K square is a constant, and D2Q by Q d phi squared, we call it minus a nu square, where a nu square is a constant. So we get three equations now. The first is the Z equation, and the second is the Q, which is function of phi, and the third is, we call it the radial equation. The Z equation has the exponential solutions, and the Q equation, which depends on phi, has this type of solution. For phi to be single valued, that's Q of phi plus 2 pi equal phi of 2 pi leads to a new integer. That's nu must be integer in this case. Now let's take the radial part and change of variables by writing rho as x over k and write the derivatives, the first and the second derivatives in terms of x. We get this expression. This is how to go from x to rho, from rho to x. We get this equation in the box. We call it Bessel equation. Now the solution, we will solve it around x equals 0. X equals 0 is a regular singular point. The solution has this form. This is Fairbairn's method of solving such type of equations. Now we take the first and the second derivative and substitute in this Bessel equation, and we get this expression. Now for the first term is the j equals 0. We call it the initial equation, which has a solution alpha equal plus or minus a nu, or alpha square equal a nu square. Then we move to j equal 1. We get second expression in terms of a1. This is the for j equal 1. When we simplify, we get this expression. But if alpha is not equal to minus 1, this minus half, this is minus half, we get a1 equal 0. Now for the jth equation, we get this long expression, and substituting for alpha square equal a nu square, simplifying, we get this recurrence relation, a sub j equal this term. Now we know that a1 equals 0, so using the recurrence relation, all odd terms are zeros. Now we left with the even number, with j as an even number, even integer or even number. By letting j equal 2n, we get this expression for the recurrence relation. You push this 2 outside, we get 4n into alpha plus n in the denominator. So now replace n here by j, we get this recurrence relation where j now can be 1, 2, 3, etc. Now we make a reduction until we get a0. a0 is a constant, a0 is a constant, and 0 is an even integer. Finally we get this expression for a sub 2j. Now we multiply the whole thing by 1, which is alpha factorial by alpha factorial. We get this expression for a sub 2j, simplifying to get this. Now substitute back into series, which is this expression. Now j is 2j, and you run from 0, j runs from 0 to infinity, a sub 2j x to the power 2j, but x e to j is this given by this expression, and our alpha is by plus nu or minus nu. Therefore we have two solutions. Now this is, we have to choose a0 for purpose of normalization. We put a0 equal to the power alpha times gamma of alpha plus 1, since it's an arbitrary constant. We get these two expressions. We call these two expressions Bessel functions of first kind. Now, if nu is integer in the Bessel function, then g nu and j minus nu are dependent, and they are no longer we need in this case another solution, a second solution for the Bessel function, for the Bessel equation. Now this is, in this slide I am showing that j minus nu is some constant times j of nu. It means that it's dependent on each other. Substitute instead of j minus nu by s, and then we get this expression. Now this expression minus 1 to the power nu, push it outside because the sum depend on s. So we have minus 1 to the power nu times this j sub nu. Now here in this expression we call nu as m to indicate that it's an integer. So we get j minus m is nothing but a constant times j sub m. In this case it means that they are linearly dependent. You put one as a constant times the second. Now for the second solution, I am not going to show that because it takes time. We call it Bessel function of second kind, which is a Newman function. It's a linear combination of j sub nu and j minus nu, which is given by this expression. Now these two functions are now linearly dependent, and nu is a second solution whether nu is constant, is integer or not. Now again here I am writing the first kind, and this is the case of m equal integer, and this is the Bessel function or Newman function. Now if we substitute a new integer, we take the limit as a new as integer, we get 0 by 0. Using L'Hopital's rule, we get this expression for n sub nu. Now we can make another kind of Bessel functions, which is called third kind, by a linear combination of j nu and n nu. The first kind is j sub nu plus I n nu, and the second kind h nu2 is j nu minus I. We replace I by minus I. This is the complex conjugate of the first. Now some recurrence relation for this cylindrical function is given by this expression, and this is another expression. Now here I am showing some of the limiting cases for small arguments of the cylindrical function j sub nu. It approaches this expression. For n, it's given by this, where n equals 0, nu equals 0, and this is for this expression for nu does not equal to 0. N is non-negative in this case. Now for large arguments of j sub nu, we get this expression. This we call it asymptotic behavior, and for n sub nu is this. Here I am showing the n of 0 versus x. You see there are some roots for this n of 0, This is for j of 0. This is the first root, second root. We will see in the next lecture that these roots form a complete set. Now, in this slide, I'm showing a second method how to find the second solution from the first solution. And this is an example in case of a nu equal 0. We know j sub nu is the first solution. So n0 is given by this. You substitute in this equation. And then we get this expressions. So it behaves like a logarithmic function. In this equation, I'm showing some generating function involves Bessel function, which is given by x over 2 e to the power x over 2 times this expression equals sum from minus infinity to plus infinity j sub m of x t to the power m, where m is integer. A useful relation is to put this t and this equal to I to the power theta. We get this expression. This will lead to integral expression of Bessel function. Thank you.